Let's attempt another one, which is member. Now is member checks if a given atom is a member of a list. Now how do we do this? It's very similar to lat. Now let's try to see how to do this. So let's say a list that is passed to us is 1 2 3 4, and we want to check if uh, 3 is a member of this list. So we extract the first element and then we check, okay, if the first member is equal to the element that we are looking for. It's not. So if it was, then we can just return true at that point. If it's not, then we need to continue to check the remainder of the list. So here the way we can do this is to invoke the isMember function on the remainder of the list, just 2 3 and 4. As you can see, at some point it will reach a stage where the list is reduced to this, and then eq ends up finding the element that we are looking for. It ends up finding the element that we are looking for. So it, we can work it out this way. Again, the end condition is nothing but if the list is empty, we return false because we cannot find an element in an empty list. So let's code this. Const is member, looking for an element k in list S. The end condition first. If is empty of S, if the list is empty, we return false. Else, let's extract the first element and the remainder of the array. Now, at this point, if the first element is equal to x, what we've been looking for, then we just need to return true. Otherwise, thus an or, otherwise we need to continue looking for the member that we want in the remainder of the list, and the remainder of the list is xs. Cool. So let's check if this works. It's member 4 2 3 4 5. Cool, that works. So let's look for some element which is not there, which should return false. Yeah, that works. Nice. So we, we were able to define something like isMember using recursion in a very intuitive way. If the list is empty, the end base condition is if the list is empty, we return false because the element cannot be present in an empty list. Otherwise, we extract the first element and the remainder. So we first check if the first element is equal to the member we've been looking for. If yes, then it just returns. So remember, or always short circuit, so it will just return here. Otherwise, or we go ahead and look for the member in the remainder of the list. So this is a problem which is defined by me. I call it the descending member. Now there's a slight twist on this isMember. Now what if the list contains other lists and possibly those lists contain other lists? How are we going to do this? So an example is, let's say we have a list which is like this. 2 has another list which has another list which has another list which has 4 and 6, 7. So let's say this is the list and we are looking for 6 in this structure. So it has to first check if, okay, 6 is equal to 2. No, 6 is not equal to 2. So it moves on to the next element. The next element is this list. So now the idea is that we need to descend into this list and check if 6 is contained in this list. So it descends into this list and says checks for 3, then if not, it goes to check the next one, which is this 5 and 4. It's not contained in that. So it's once that way it will exhaust all of this, and it ultimately descends into this list and it exhausts that. Now at that point it needs to continue looking at the next element, which is, so it will be in this list and it has exhausted 5 and 4, and at that point it needs to continue to look at this, and here it's equal, right? So this gives us some idea about how we might do this. Now this is very similar to isMember, but the difference is that if an element is not an atom but a list, we need to descend into that list. So let's see how to do that by modifying the isMember function. So let's call this as descending member. Now the end condition remains the same. If it is empty, we return false. Otherwise, we break the array, we get the first element and the remainder of the remainder of the list, and we check if the element that we have got, the first element that we got, x is equal to k that we are looking for. Now if it is, we return here as earlier, or will short circuit. So if it is true, then we just return here, which is all good. But if it is not, equal, then there are two possibilities. The possibility is that x is an atom, and in that case we just need to continue checking the remainder of the list, which is xs. This is similar to isMember k of k, where we looked for isMember and in the remainder of the list, because every element here was an atom. But if it is not an atom and if it's a list, then we need to descend into that list. So is atom, so if it is not equal, then we need to first check if x is an atom. Now if x is an atom, then it's nothing, it's quite simple, it's nothing but we need to continue to look for x in the remainder of the list. But if it's not, and if it is a list, then what do we do? If it's not, then we need to descend into that list. So we need to look for the element in x, which is a list. Now not only that, let's say if we look into that list. So an example was here. Okay, sorry, let's take an example. So we have 2, 3, and let's say we have 4, 5, and 6. So here it looks for 2, which is not equal, 3, which is not equal, and then at this point it encounters 4 and 5, where because list of 4 and 5 is not an atom, we come here and then we say, okay, let's look for the element in now this list, which is x, which is nothing but 4 and 5, and then we realize that it's not there. But once we have looked into that, what do we need to do is we need to be able to look into the next element of the original list, the parent list, which is nothing but 2 3, this one 2 3, and we need to continue to look as the next element, which is nothing but 6. So if the element is not present in the child list, we'll continue to look for the member in the remainder of the parent list. And if it is a list, then it's, if let's say even the first member of xs is a list, so this logic can continue, and this will keep descending into the child list, and if the element is not found, then it comes back and continues with the next elements, next remainder of the list of the parent list. uh, it's a bit uh, complex to take in, but if you work out some examples, you will be able to see why this makes an intuitive sense, and why this definition makes sense and it will work. Now let's check if this works. Now let's first give a simple example of a, a plain list. So 4, let's look for this, 1 2 3 4 5, this should return true. Yeah, that works. Now let's make this list a bit complicated. Now let's say the second element is in fact a list, right? And then let's complicate it even further. 3 6 and then 4. So 4 is present in the second level. Yeah, that works. Now let's look for some element which is not present. This return false. Yeah, so that works. So now if you think about it, how it works is, let's work this out. Now we're going to call for this descending member. So first it will extract the extract 1. So x is nothing but xxx is nothing but 1, and then the remainder of the list, which is nothing but 2 3, this one. Now obviously k4 is not equal to 1, so it moves to the remainder of the list. Now it invokes descending member on the remainder of the list, which is this one. At this point, x and xs are equal to 2 and the remainder of the list. So 2 is not equal, so then it invokes descending member on the remainder of the list. Just a minute. Sorry. So at this point, it invokes on this one. Two, three. Yeah. Here there's a mistake which I did. Yeah. So now x is nothing but x is this list now, and the remainder of the list is 5. Xs is 5. So x is this list, and xs remainder list is 5. Now eq is invoked on this one. Check if 4 is equal to this, so it's not equal to. Then we check if this x is still an atom. It's not an atom. Because it's not an atom, we end up here, which is checks if descending member, and we descend into the list. So we descend into invoking, looking for 4 into the child list, which is this. At this point, x is equal to 2 and xs is equal to the remainder of the list, which is nothing but this. So x is not equal to, and sorry, 4 is not equal to 2. So we end up going here, which is descending member k of x's. We end up looking it in the remainder of the list. So descending member now becomes, it gets invokes on 4 and 3, 6 and 4. At this point, again, because the first element is 3 and 6, and because it's not an atom, it will end up invoking on descending member check on this one, and as you can see, this is going to return false. At some point the list is going to become empty and we're going to return false. But now the thing is, see, we have looked at 3 and 6, but we had to continue to look at the parent list. The parent list is not complete. We have not completely looked at the parent list, and this is where our remaining element 4 is. So this is where this OR condition comes into picture. We need to continue to look at the member in the remainder of the parent list if the child list does not have it. So if you work out a few examples of this, it will start to make sense. The way I would say, how do we come up with this is to attempt to solve a few examples, variations of examples, and then try to work through the problem, and then you will be able to come up with an intuitive definition of the recursive solution. So thank you for watching this video. We are going to continue this series. In the next few videos, we are going to solve more recursive problems and more interesting recursive problems. Thank you for watching.